Every atom in your body has a perfect opposite twin. These twins want to destroy each other completely. Most people think antimatter only exists in sci-fi movies. That's spectacularly wrong. Tonight we're discovering the shocking evidence for these cosmic twins. You'll learn why they represent the most dangerous substance possible. Before we dive into this mirror universe, drop a comment about what you think happens when twins collide. If you enjoy these reality-bending science journeys, consider subscribing. These explorations of the impossible are meant to be shared. For decades, physicists thought they understood matter completely. Every atom contained the same basic building blocks. Tiny particles with specific electrical charges. Scientists felt confident about this simple picture. Then someone noticed impossible tracks in a detector. A researcher named Carl Anderson was studying high-energy particles from space in 1932. His device captured photographs of particle paths. Most tracks curved in predictable directions based on their electrical charge. But one track curved the wrong way entirely. This particle carried the same mass as an electron, but its electrical charge pointed in the opposite direction. Anderson had discovered what we now call a positron, the electron's evil twin. This shattered the foundation of physics. Matter doesn't come in just one form. Every fundamental particle has a perfect opposite partner waiting somewhere in the universe. Today's giant machines that smash particles together prove this daily. When scientists create new particles in high-energy collisions, twins always emerge together. The universe never breaks this rule of perfect pairing. Pure energy can transform into matter and antimatter pairs. This happens through a process scientists call pair creation. Think of it as the universe's most expensive magic trick. Einstein's famous equation works both directions. Matter becomes energy when particles destroy each other. Energy becomes matter when conditions are just right. The universe demands enormous payment for this transformation. Creating just one electron and its antimatter twin requires incredibly powerful energy, more than twice the particle's mass converted to pure power. This happens constantly around us. High-energy particles from deep space strike our atmosphere every second. These cosmic bullets trigger showers of new particle pairs. Thousands of matter-antimatter twins emerge from each collision. Even empty space participates in this cosmic dance. The vacuum itself churns with virtual particle pairs that pop into existence and vanish almost instantly. These ghost twins appear for impossibly brief moments before destroying each other. This reveals matter's deepest secret. Existence requires partnership. The universe never creates matter alone. Storing antimatter represents one of science's greatest challenges. These particles want to annihilate instantly when they touch normal matter. Scientists need invisible cages to keep them isolated. Magnetic fields create these invisible prisons. Powerful electromagnets suspend charged antimatter particles in mid-air. The particles float without touching any physical walls. Even a single contact with normal matter triggers complete destruction. Scientists also use a combination of electric and magnetic fields to trap particles in specific locations. These electromagnetic cages can hold antimatter for minutes or even hours. That might not sound impressive, but it represents a tremendous achievement. The storage environment must be nearly perfect vacuum. Even a few stray gas molecules spell disaster. When antimatter encounters any normal matter, both particles vanish completely and release tremendous energy. Today's most advanced facilities can store only tiny amounts of antimatter. The total quantity held in all laboratories worldwide equals just a few dozen atoms. Each storage success represents years of careful engineering and precise control. Space contains vast antimatter factories operating constantly. These cosmic facilities dwarf anything humans have built on Earth. They produce antimatter through violent astronomical processes. High-energy particles from distant stars crash into our atmosphere daily. These cosmic rays carry tremendous energy from their journeys across the galaxy. When they collide with air molecules, they trigger antimatter creation on a massive scale. Exploding stars generate antimatter through their death throes. The intense heat and pressure during stellar explosions create perfect conditions for matter-antimatter pair production. These cosmic catastrophes scatter antimatter particles across space. Even our Sun participates in antimatter manufacturing. Solar flares release powerful magnetic fields that accelerate particles to incredible speeds. These energetic collisions produce antimatter in the Sun's outer atmosphere. The most extreme antimatter factories exist near black holes. These cosmic monsters accelerate matter to nearly the speed of light. The incredible energies involved create vast quantities of antimatter particles that jet outward into space. When matter and antimatter particles collide, they achieve the most complete destruction possible in our universe. Both particles vanish entirely and convert to pure energy. This process is called annihilation. The conversion follows Einstein's famous equation perfectly. Even tiny amounts of matter release enormous energy when destroyed completely. A single gram of antimatter annihilating with normal matter produces more energy than nuclear explosions. The destruction happens at the speed of light. When an electron meets a positron, both particles disappear instantly. They transform into high-energy light particles called gamma rays. No trace of the original matter remains. This represents the most efficient energy release known to science. Chemical reactions convert less than 1% of matter to energy. Nuclear reactions convert slightly more. Antimatter annihilation converts 100% of matter to energy. The universe maintains perfect symmetry in these encounters. Equal amounts of matter and antimatter always destroy each other. The energy released depends exactly on the total mass involved. Nature keeps precise accounts in this cosmic transaction. Antimatter has quietly revolutionized modern medicine. Hospitals use antimatter-powered scanners to peer inside human bodies without surgery. These machines rely on controlled antimatter annihilation to create detailed images. The process begins with radioactive materials that naturally produce antimatter. These substances release positrons, antimatter electrons, as they decay. Medical technicians inject tiny amounts of these materials into patients. When the antimatter particles encounter electrons in human tissue, they annihilate instantly. This destruction produces gamma rays that escape the body. Special detectors capture these energy signatures from outside. Computer systems analyze the gamma ray patterns to construct detailed images. Doctors can observe blood flow, brain activity, and tumor locations with incredible precision. This technique is called positron emission tomography. The antimatter doses are incredibly small. Patients receive only tiny amounts of radioactive material. The antimatter particles annihilate so quickly they cannot cause harm. This represents antimatter's most practical application today. Millions of medical scans rely on antimatter technology every year. What was once pure science fiction now saves lives in hospitals worldwide. Creating useful amounts of antimatter faces overwhelming technical challenges. Current production methods require millions of times more energy than the antimatter provides. This makes antimatter the most expensive substance on Earth. The world's most powerful particle accelerators can produce only tiny quantities. Creating enough antimatter to power a light bulb for 1 second would require running these machines for millions of years. The energy costs are astronomical. Storing antimatter presents equally daunting challenges. Scientists have managed to confine antimatter for only a few hours under perfect laboratory conditions. Any technical failure results in immediate annihilation and energy release. The quantities involved reveal the scale of the problem. All the antimatter ever created by humans combined weighs less than a single grain of sand. Producing enough antimatter for practical applications would require revolutionary breakthroughs. Safety concerns add another layer of complexity. Even microscopic amounts of antimatter release dangerous energy when they annihilate. Larger quantities would pose risks that current technology cannot manage. These barriers explain why antimatter remains confined to research laboratories and medical applications. The gap between scientific possibility and practical reality remains enormous. Antimatter represents the ultimate energy source for humanity's future. When technical barriers finally fall, antimatter could revolutionize space travel and solve Earth's energy crisis. The potential applications stretch beyond current imagination. Antimatter rockets could accelerate spacecraft to significant fractions of light speed. This would reduce interstellar journey times from millions of years to mere decades. Antimatter propulsion could open the entire galaxy to human exploration. The energy density of antimatter dwarfs all other power sources. A few grams of antimatter contain more energy than millions of tons of chemical fuel. This could provide clean, inexhaustible energy for human civilization. Antimatter might enable technologies that seem impossible today. Terraforming planets, manipulating matter at the atomic level, or even powering time dilation effects for extended space journeys. The applications would reshape human existence. However, these advances require breakthroughs that may take centuries to achieve. Scientists first solve the fundamental problems of efficient production and safe storage. The technical challenges remain staggering. Until then, antimatter's role stays limited to scientific research and medical applications. But the potential rewards justify continued investigation into this mirror universe of particles. Mastering antimatter could mark humanity's transition to a truly cosmic civilization. What happens when pure energy decides to become matter? This question puzzled physicists for decades. They knew energy and matter were connected, but watching the actual transformation seemed impossible. Then scientists discovered they could photograph the birth process itself. High-energy light rays can transform directly into particle pairs. This process requires incredibly powerful light, far more energetic than anything our eyes can see. Scientists call these supercharged light particles gamma rays. When a gamma ray encounters the powerful electric field near an atomic nucleus, something extraordinary occurs. The pure energy suddenly splits into two solid particles. An electron and its antimatter twin appear simultaneously. This represents the universe's most fundamental magic trick. Pure energy becomes solid matter in the blink of an eye. Both particles emerge with identical mass but opposite electrical properties. The process works like cosmic alchemy. Energy flowing through space suddenly crystallizes into two perfect twins. This transformation happens everywhere in the universe where sufficient energy meets the right conditions. Creating matter from energy demands an astronomical energy budget. The universe enforces strict minimum payments for this cosmic transaction. No shortcuts exist in this fundamental accounting system. Scientists discovered the exact price through careful experiments. Creating an electron-positron pair requires gamma rays carrying specific energy, exactly 1.02 million electron volts. This represents twice the electron's mass converted to pure energy. Think of it as the universe's layaway plan. You must pay the full price up front before receiving your matter twins. The energy payment goes directly into creating the particle's mass and motion. Heavier particles demand even higher energy payments. Creating a proton and antiproton pair costs nearly 2,000 times more energy than electron pairs. The universe charges premium prices for heavyweight particles. This energy requirement explains why antimatter creation remains so difficult. Gathering enough concentrated energy to trigger pair production requires enormous machines and massive power consumption. Look at any patch of seemingly empty space. Your eyes see absolute nothingness. But quantum physics reveals a completely different reality hidden beneath this calm surface. The vacuum itself churns with constant particle creation and destruction. Virtual particle pairs pop into existence everywhere, every instant. These ghost twins live for impossibly brief moments before vanishing. Scientists call this phenomenon vacuum fluctuations. The empty space between atoms contains more activity than a busy intersection. Countless particle-antiparticle pairs appear and disappear faster than any detector can measure. These virtual particles borrow energy from the universe's quantum bank account. They must repay this energy loan almost instantly by annihilating each other. The universe permits this borrowing only for microscopic time periods. This hidden reality transforms our understanding of emptiness. What appears to be vacant space actually teems with particle ghosts. The vacuum represents one of nature's busiest neighborhoods. Modern physics laboratories contain the most powerful machines humans have ever built. These particle accelerators stretch for miles underground. But their purpose differs completely from what most people imagine. Scientists don't use these machines to study tiny particles directly. Instead, they create controlled cosmic crashes. High-energy protons race through magnetic tunnels and collide with incredible force. These collisions recreate conditions that existed moments after the universe began. The tremendous impact energy transforms into cascades of new particles. Matter and antimatter pairs emerge from each crash like sparks from a cosmic anvil. The largest accelerator can generate thousands of antimatter particles per second. This might sound impressive until you realize the enormous energy cost involved. The machine consumes enough electricity to power entire cities. Each antimatter particle costs millions of times more energy to create than it will ever provide. These facilities represent the ultimate example of expensive manufacturing processes. Right now, invisible bullets are striking Earth's atmosphere above your head. These cosmic ray particles travel nearly the speed of light. They carry more energy than anything humans have created in laboratories. When these cosmic bullets hit air molecules, they trigger spectacular chain reactions. The enormous collision energy creates avalanches of new particles. Thousands of matter and antimatter pairs emerge from each impact. These particle showers rain down continuously across the entire planet. Every square inch of Earth receives cosmic ray impacts every second. Most particles are harmless by the time they reach the ground. The atmosphere acts as a natural particle accelerator more powerful than any human machine. Cosmic rays deliver energy levels that dwarf our most advanced laboratory equipment. Space provides unlimited fuel for these cosmic collisions. This process has operated continuously for billions of years. The cosmic ray bombardment helped shape the early evolution of life on Earth. Our planet exists within a constant antimatter production zone. Certain unstable atoms manufacture antimatter as they fall apart. This happens through a natural process scientists call radioactive decay. These atomic breakdowns accidentally produce antimatter particles. The process begins with atoms that contain too many protons for stability. These overloaded nuclei must shed excess positive charge to achieve balance. They accomplish this by converting a proton into other particles. During this transformation, a proton turns into a neutron, a positron, and a nearly weightless particle called a neutrino. The positron represents antimatter created entirely by natural atomic processes. Medical facilities exploit this natural antimatter production for diagnostic scanning. They inject patients with substances that decay and release positrons. These antimatter particles immediately annihilate with electrons in human tissue. The annihilation produces gamma rays that escape the body and create detailed images. This represents antimatter's most practical application in modern medicine. Nature's accidental antimatter production saves human lives. Can magnetic fields create matter from empty space? This question sounds like science fiction. But the most extreme magnetic environments in the universe actually accomplish this impossible feat. Neutron stars possess magnetic fields trillions of times stronger than Earth's magnetosphere. These stellar remnants compress matter to incredible densities while generating unimaginable magnetic forces. The combination creates perfect conditions for vacuum manipulation. The ultra-strong magnetic fields literally squeeze virtual particle pairs out of empty space. Normally, these quantum fluctuations appear and disappear instantly, but extreme magnetism can separate the partners before they annihilate. This process converts virtual particles into real matter and antimatter. The magnetic field provides the energy needed to make temporary particle pairs permanent. Empty space becomes a source of actual particles. Scientists hope to recreate these conditions in laboratory experiments. Generating sufficiently strong magnetic fields requires technology that doesn't yet exist. But the theoretical possibility opens new avenues for antimatter production. Black holes represent the most extreme environments in the universe. But their strangest property might be their ability to manufacture particles from nothingness. This process defies common sense about cosmic monsters that supposedly devour everything. The space immediately surrounding black holes experiences tremendous distortion. Gravity becomes so intense that it actually tears apart the fabric of reality itself. This creates conditions unlike anywhere else in the universe. Virtual particle pairs that normally annihilate instantly find themselves separated by the black hole's gravitational field. One partner falls past the point of no return while its twin escapes into space. The surviving particle becomes real matter or antimatter. Scientists call this phenomenon Hawking radiation. The black hole effectively pays the energy cost to convert virtual particles into real ones. This process causes black holes to slowly evaporate over cosmic time periods. This represents the universe's most exotic antimatter factory. The same objects that destroy everything they touch also create new particles from empty space. Nature's extremes often produce seemingly contradictory results. The universe began as pure energy concentrated in an impossibly small space. During the first microseconds after the Big Bang, temperatures soared beyond current comprehension. These extreme conditions triggered the most massive particle creation event in cosmic history. Energy densities during this primordial epoch dwarfed anything seen since. The entire universe functioned as a gigantic particle accelerator. Every cubic inch of space churned with continuous matter and antimatter creation. Perfect symmetry ruled this early cosmos. Equal amounts of matter and antimatter emerged from the energy soup. For brief moments, the universe contained perfect balance between these cosmic twins. Then something extraordinary occurred that physicists still don't fully understand. A tiny imbalance developed between matter and antimatter production. For every billion antimatter particles, the universe created 1,000,000,001 matter particles. This microscopic asymmetry determined the fate of everything. When the universe cooled enough for particles to survive, matter and antimatter annihilated completely. Only the tiny matter surplus remained to form planets and ultimately life itself. Today's most advanced antimatter facilities operate with stunning inefficiency. Creating useful quantities of antimatter remains impossibly expensive using current methods. The energy requirements dwarf any practical power source. The world's most powerful particle accelerators can produce only nanoscopic amounts of antimatter. Generating enough antimatter to power a small light bulb would require running these machines continuously for millions of years. The electricity costs alone would bankrupt nations. Storage represents an equally daunting challenge. Scientists have managed to contain antimatter for only hours under perfect laboratory conditions. Maintaining the ultra-high vacuum and magnetic containment systems consumes enormous energy. Current antimatter production efficiency hovers near 0.001%. For every joule of energy invested, Scientists recover less than a millionth of a joule in antimatter. This represents the worst energy return on investment in human technology. These limitations explain why antimatter applications remain confined to medical imaging and physics research. The gulf between theoretical possibility and practical reality spans orders of magnitude that may require centuries to bridge. Scientists face an impossible storage problem. Antimatter destroys any container it touches. Traditional storage methods become instantly lethal when dealing with these cosmic twins. The solution involves invisible walls made of pure magnetism. Powerful electromagnets create magnetic bottles that hold charged antimatter particles suspended in empty space. These invisible containers have no physical walls. The particles float freely without touching anything solid. Think of it as a magnetic cage with bars made of force fields. Charged particles follow magnetic field lines like trains on invisible tracks. Scientists can steer and contain antimatter using these magnetic highways. The magnetic bottle technique works only with electrically charged antimatter particles. Positrons and antiprotons respond to magnetic forces. Scientists can push and pull these particles using carefully controlled electromagnetic fields. This represents humanity's first practical method for antimatter storage. The technique allows scientists to hold small quantities of antimatter for extended periods without immediate annihilation. Storage scientists discovered that combining two different forces creates superior particle cages. Electric fields and magnetic fields work together like a cosmic team. This partnership produces the most stable antimatter confinement possible. The device scientists call an ion trap uses both electric and magnetic forces simultaneously. Electric fields create potential energy valleys where particles naturally settle. Magnetic fields prevent the particles from escaping these electrical valleys. Picture a bowl made of invisible energy. Antimatter particles roll into the bottom and stay trapped. Electric forces create the bowl shape. Magnetic forces prevent the particles from climbing out. These combination traps can hold antimatter particles in precisely defined locations. Scientists control the trap strength by adjusting the electrical and magnetic field intensities. Stronger fields create deeper energy valleys. The dual-force approach provides redundant containment systems. If one force field fails, the other continues holding the antimatter. This backup system prevents catastrophic storage failures that would destroy expensive laboratory equipment. Antimatter requires the purest vacuum humans can create. Even a few stray air molecules spell disaster for antimatter storage attempts. Scientists must eliminate virtually every trace of normal matter from storage chambers. Creating ultra-high vacuum means removing air molecules one by one. Standard room air contains trillions of molecules per cubic inch. Scientists must reduce this to fewer than 1,000 molecules per cubic inch. Powerful vacuum pumps work continuously to suck out remaining gas molecules. Multiple pump systems operate in series to achieve progressively cleaner vacuum conditions. Each pump stage removes different types of contaminating particles. The vacuum quality determines antimatter storage success. Better vacuum means longer storage times and reduced particle losses. Poor vacuum leads to rapid antimatter annihilation and storage system failure. Even microscopic traces of oil, dust, or water vapor destroy antimatter instantly. Storage chambers require surgical cleanliness levels that exceed medical operating room standards. Contamination control becomes absolutely critical for antimatter research. Hot antimatter particles move too quickly for stable storage. Rapid motion makes magnetic and electric containment extremely difficult. Scientists needed methods to slow down antimatter particles without destroying them. Laser cooling provides the solution through a counterintuitive process. Special laser light actually reduces particle motion rather than heating things up. This technique can slow antimatter to crawling speeds. The process works by hitting particles with precisely tuned laser photons. Each photon collision removes a tiny amount of motion energy from the antimatter particle. Millions of laser impacts gradually slow the particles down. Cooled antimatter becomes much easier to control and store. Slow-moving particles respond better to magnetic and electric containment forces. Lower temperatures also reduce the accidental particle collisions. Scientists can cool antimatter to temperatures approaching absolute zero, the coldest possible temperature in the universe. At these extreme temperatures, antimatter particles barely move at all. Neutral antimatter atoms create storage nightmares for scientists. These particles carry no electrical charge. They ignore magnetic and electric fields completely. Traditional containment methods become useless. Antihydrogen atoms represent the simplest neutral antimatter. Each atom contains one antiproton and one positron orbiting together. The positive and negative charges cancel out perfectly. Scientists cannot push, pull, or steer these neutral atoms using electromagnetic forces. The particles drift freely through magnetic bottle traps. Electric fields have zero effect on neutral antimatter motion. Storage solutions for neutral antimatter require entirely different approaches. Scientists explore gravitational traps, laser manipulation, and exotic matter wave techniques. None of these methods work reliably yet. The neutral antimatter storage problem remains largely unsolved. Current techniques can hold neutral antimatter for only minutes under perfect conditions. Most neutral antimatter escapes containment and annihilates almost immediately. Modern antimatter storage operates under severe time constraints. Current world record storage times measure in hours, not days or weeks. These brief storage periods limit practical antimatter applications. One famous antihydrogen containment milestone lasted approximately 16 minutes. This required perfect vacuum conditions, ultra-stable magnetic fields, and continuous active control systems. Even tiny disturbances cause immediate storage failure. Storage time depends critically on environmental stability. Temperature fluctuations, mechanical vibrations, and electromagnetic interference all reduce containment duration. Laboratory conditions must remain absolutely steady. Most antimatter storage attempts last only seconds or minutes before particle losses become overwhelming. Scientists consider storage times over 1 hour to be exceptional achievements worthy of scientific publication. These time limitations prevent antimatter accumulation for practical applications. Using antimatter as fuel or energy storage requires containment periods measured in months or years. Current technology falls drastically short of these requirements. Temperature control represents a critical factor in antimatter preservation. Hot particles move rapidly and escape containment easily. Cold particles move slowly and stay trapped longer. Scientists cool antimatter storage systems to temperatures approaching absolute zero. Absolute zero represents the coldest possible temperature, the point where all atomic motion stops. Reaching these extreme temperatures requires sophisticated refrigeration systems. Cryogenic cooling systems use liquid helium and specialized refrigeration cycles to achieve ultra-low temperatures. These systems consume enormous amounts of energy to maintain the necessary cold conditions. Cold antimatter particles have less kinetic energy to overcome magnetic and electric containment forces. Reduced particle motion dramatically improves storage stability and duration. Lower temperatures also reduce collision rates between different antimatter particles. The cooling systems must operate continuously throughout the storage period. Any warming causes immediate particle motion increases and rapid storage degradation. Maintaining extreme cold becomes essential for antimatter preservation. Does antimatter fall up or down in Earth's gravity? This fundamental question has puzzled physicists for decades. The answer could revolutionize our understanding of gravity and space-time. Scientists expect antimatter to fall downward just like normal matter. Einstein's general relativity theory predicts that all forms of matter and energy respond identically to gravitational fields. Antimatter should follow the same rules. Physicists have long tested whether antimatter might behave differently in gravity. If it did, that would represent one of the most revolutionary discoveries in modern physics. Testing antimatter's gravitational response requires incredibly sensitive experiments. Earth's gravity produces tiny forces compared to electromagnetic effects. Isolating pure gravitational influences demands extreme precision. Current experiments use neutral antimatter atoms to eliminate electromagnetic interference. Scientists drop antihydrogen atoms in carefully controlled conditions and measure their motion with laser interferometry. The results help refine how closely antimatter matches conventional gravitational laws. How much antimatter have humans created throughout history? The answer reveals the staggering difficulty of antimatter production and storage. The amounts humans can store remain microscopic by any practical standard. The total quantity of stored antimatter across laboratories worldwide remains tiny. This represents an essentially negligible amount of actual matter. Individual antimatter storage experiments typically contain between 1 and 10,000 particles. These microscopic quantities require enormous machines, massive energy consumption, and teams of scientists to maintain. Each stored antimatter atom costs millions of dollars to create and preserve. The storage quantities reflect fundamental technological limitations rather than safety concerns. Current production and containment methods cannot scale up to larger amounts. Creating visible quantities of antimatter remains beyond human capabilities. These minimal storage amounts explain why antimatter applications remain confined to basic research and medical imaging. Practical antimatter use requires quantities thousands of times larger than current storage achievements. Even microscopic amounts of antimatter pose serious safety risks during storage failures. When containment systems malfunction, antimatter annihilates with surrounding materials and releases intense gamma radiation. Laboratories require extensive safety protocols to protect researchers. Antimatter storage facilities operate behind multiple layers of radiation shielding. Thick concrete walls and lead barriers absorb gamma rays produced during accidental annihilation events. Warning systems alert personnel when containment parameters drift outside safe ranges. Remote operation systems allow scientists to control antimatter experiments from safe distances. Robotic manipulators handle delicate storage equipment without exposing humans to radiation risks. Video monitoring provides real-time observation of containment systems. Emergency shutdown procedures can terminate antimatter experiments instantly when dangerous conditions develop. Automated systems monitor storage parameters continuously and trigger protective responses faster than human operators could react. Despite these precautions, antimatter research remains inherently dangerous. Storage system failures can damage expensive equipment and create radioactive contamination. The combination of cutting-edge technology and exotic matter requires constant vigilance and rigorous safety protocols. The safety challenges illustrate why antimatter applications remain limited to specialized research facilities. Practical antimatter use would require safety systems far beyond current capabilities. The risks currently outweigh the potential benefits for most applications. Invisible bullets strike Earth's atmosphere constantly above your head. These cosmic ray particles travel nearly the speed of light after journeying across the galaxy. Each impact triggers spectacular antimatter creation. High-energy protons from distant stars crash into air molecules 20 miles above the ground. The collisions release more energy than humanity's most powerful machines. This cosmic bombardment operates continuously across the entire planet. Each cosmic ray impact creates cascading showers of new particles. The original collision spawns dozens of secondary impacts. Each subsequent crash produces more matter-antimatter pairs in an expanding cascade. Think of it as a cosmic pinball machine. One high-energy ball triggers multiple collisions throughout the atmosphere. Thousands of antimatter particles emerge from each initial cosmic ray strike. This natural antimatter production dwarfs all human manufacturing efforts. Space delivers unlimited fuel for these cosmic particle accelerators. Earth exists within a constant antimatter rain that most people never notice. Astronomers occasionally detect the most powerful explosions in the observable universe. These gamma-ray bursts release more energy in seconds than our sun produces in millions of years. The extreme conditions create perfect antimatter factories. These cosmic catastrophes occur when massive stars collapse into black holes or when ultra-dense stellar remnants collide. The gravitational collapse concentrates enormous energy into incredibly small regions of space. The intense energy density triggers massive particle creation events. Matter and antimatter emerge in equal quantities from the gamma-ray fireball. These explosions temporarily outshine entire galaxies containing billions of stars. Scientists can detect gamma-ray bursts from across the observable universe. Their high-energy signatures remain visible across enormous cosmic distances. These cosmic beacons reveal the most energetic processes known to physics. The antimatter production during gamma-ray bursts exceeds anything possible on Earth. Nature routinely achieves energy concentrations that dwarf humanity's most ambitious engineering projects. Imagine a star that weighs more than our sun but measures only 12 miles across. Now imagine this ultra-dense object spinning 30 times per second. These cosmic tops create the most powerful magnetic fields in the universe. Scientists call these objects pulsars. They are the rapidly spinning remnants of exploded stars. Each pulsar contains more matter than our sun compressed into the size of a city. The extreme density creates unimaginable physical conditions. The spinning creates magnetic fields trillions of times stronger than Earth's magnetosphere. These intense magnetic forces literally tear apart the fabric of empty space around the pulsar. Virtual particle pairs get separated before they can annihilate. The magnetic field provides the energy needed to convert temporary quantum fluctuations into real particles. Empty space becomes a source of actual antimatter near these cosmic lighthouses. The process operates continuously as long as the pulsar keeps spinning. This represents one of nature's most exotic antimatter manufacturing processes. The same objects that mark stellar death sites also create new particles from pure nothingness. Black holes seem like cosmic monsters that destroy everything they encounter. But the space immediately surrounding these gravitational giants actually manufactures antimatter through spectacular processes. This cosmic contradiction puzzles scientists. Supermassive black holes at galaxy centers possess masses equal to billions of stars. Matter spiraling toward these monsters reaches incredible speeds and temperatures. The extreme conditions create perfect environments for antimatter production. As material approaches the black hole, magnetic fields accelerate particles to nearly light speed. These high-energy collisions trigger continuous matter-antimatter creation. The antimatter gets caught in powerful jets that blast outward from the black hole's poles. These antimatter jets extend for thousands of light years into space. The streams contain more antimatter than human civilization could produce in billions of years. Black holes become the universe's most productive antimatter factories. The irony remains striking. Objects that epitomize cosmic destruction also create new particles from energy. Nature's extremes often produce seemingly contradictory results that challenge our understanding. Our sun seems far too gentle to manufacture antimatter. The steady daylight and warmth suggest a stable, peaceful star. This impression drastically underestimates the sun's hidden violent nature. Solar flares represent explosive releases of magnetic energy stored in the sun's atmosphere. These solar storms can release the energy equivalent of billions of nuclear bombs within minutes. the extreme conditions can become intense enough for antimatter production. During major solar flares, the sun's magnetic field lines suddenly reconnect and snap like cosmic rubber bands. This magnetic reconnection accelerates particles to tremendous speeds. High-energy collisions produce antimatter in the sun's outer atmosphere. Scientists have detected antimatter production during the largest solar flares. These solar storms create positrons that get trapped in the sun's magnetic field. Some antimatter particles escape and travel toward Earth. This discovery revolutionized understanding of our seemingly quiet star. Even moderate stars like our Sun can achieve the extreme conditions necessary for antimatter manufacturing during their most violent moments. Jupiter appears as a beautiful gas giant with colorful bands and swirling storms. This peaceful appearance conceals one of the most dangerous radiation environments in the solar system. The planet's intense magnetic field creates deadly particle accelerators. High-energy particles get trapped in Jupiter's powerful magnetosphere and spiral back and forth between the planet's magnetic poles. These trapped particles bounce endlessly at incredible speeds. The radiation levels would kill any spacecraft within hours. The trapped particles occasionally collide with each other at tremendous energies. These high-speed impacts create matter-antimatter pairs within Jupiter's radiation belts. The antimatter gets immediately trapped alongside the normal particles. Scientists discovered antimatter signals in data from spacecraft that briefly survived Jupiter's harsh radiation environment. The planet's magnetosphere contains more antimatter than exists in all Earth-based laboratories combined. This unexpected discovery shows that antimatter production occurs much closer to home than previously thought. Even planets in our solar system can become natural particle accelerators under the right conditions. Stellar death represents the universe's most spectacular antimatter production events. When massive stars exhaust their nuclear fuel, they undergo catastrophic collapse in seconds. The extreme conditions during stellar death throes create perfect particle factories. The collapsing star core reaches temperatures of billions of degrees while crushing matter to unimaginable densities. These extreme conditions trigger the most intense particle creation event possible outside the early universe. Massive quantities of nearly massless particles called neutrinos emerge during the collapse. Equal numbers of antimatter neutrinos accompany each normal neutrino. These ghost particles carry away most of the star's original energy. The neutrino blast from a single exploding star contains an enormous number of antimatter particles. Most of these particles pass through normal matter without interacting. They stream across the universe at nearly light speed. This stellar antimatter production dwarfs many other natural processes. A single star's death produces more antimatter in seconds than anything humanity could create. Our galaxy's central region contains a puzzling antimatter surplus that shouldn't exist. Sensitive detectors reveal far more antimatter signals than any known process can explain. This cosmic mystery has baffled astronomers for decades. The excess antimatter appears concentrated around the galactic center, where a supermassive black hole dominates the gravitational environment. Scientists expected minimal antimatter production in this region. Instead, they found antimatter levels far higher than theoretical predictions. Traditional antimatter sources cannot account for this galactic surplus. Cosmic ray collisions, stellar explosions, and black hole processes all produce insufficient quantities. Some unknown mechanism must operate near the galaxy's heart. One leading theory involves dark matter particles destroying each other and converting to antimatter. If dark matter can annihilate, it could produce the antimatter signature observed. However, this remains purely theoretical. The galactic center antimatter mystery highlights how much we still don't understand about our cosmic neighborhood. Even familiar processes can produce unexpected results when operating under extreme conditions. travel back to the universe's first microsecond after the Big Bang. Temperatures soared beyond current comprehension while all known matter existed as pure energy. These primordial conditions created perfect matter-antimatter symmetry. Every particle creation event produced identical quantities of matter and antimatter. The early universe contained equal amounts of cosmic twins in perfect balance. For brief moments, antimatter represented exactly half of everything that existed. Then something extraordinary occurred that physicists still cannot fully explain. A tiny asymmetry developed in the cosmic production line. For every billion antimatter particles created, the universe somehow produced 1,000,000,001 matter particles. This microscopic imbalance determined everything that followed. When the universe cooled enough for particles to survive, matter and antimatter annihilated almost completely. Only the tiny matter surplus survived to form stars, planets, and life. The primordial antimatter creation event represents the largest particle production process in cosmic history. Understanding this early asymmetry remains one of physics' greatest unsolved mysteries. Look up at the night sky between the stars. The darkness appears completely empty to human eyes, but sensitive radio telescopes reveal a faint glow that fills the entire observable universe. This ancient light carries traces of the early universe. The cosmic microwave background radiation represents the afterglow of the universe's early hot state. It comes from an era long after most primordial matter and antimatter had annihilated. That light has been traveling through space ever since. Originally, this radiation blazed with tremendous intensity. Billions of years of cosmic expansion have stretched and cooled it to barely detectable levels. Modern instruments can measure this fossil light from the early universe. The background radiation provides direct evidence of the universe's hot, dense beginning. Every cubic inch of space retains traces of that early epoch. The universe preserves its own ancient record. This ancient light represents one of the oldest signals in cosmic history. The afterglow continues to bathe our planet in photons, created in the young universe billions of years ago. Picture two particles meeting at nearly the speed of light. One carries positive electrical charge. The other carries negative charge. Both possess identical mass. When they touch, something unprecedented occurs. Both particles vanish completely from existence. This represents the most thorough destruction possible in our universe. No trace of the original matter remains. The particles convert entirely to pure energy according to Einstein's famous equation. Scientists call this process annihilation. The energy release follows strict mathematical rules. Even tiny amounts of matter produce energy when completely destroyed. A single electron meeting its antimatter twin releases a tiny burst of energy. This perfect conversion represents the ultimate limit of energy extraction from matter. Chemical reactions convert less than 1% of matter to energy. Nuclear reactions achieve slightly higher efficiency. Antimatter annihilation converts 100% of matter to energy. The universe maintains precise accounting during these cosmic transactions. Equal amounts of matter and antimatter always destroy each other completely. Nature permits no exceptions to this fundamental conservation rule. For decades, physicists believed the universe treated matter and antimatter with perfect equality. The fundamental laws seemed completely symmetric between cosmic twins. This assumption shaped theoretical physics for generations. Then scientists discovered subtle violations of this perfect symmetry. Certain particle interactions favor matter over antimatter by microscopic amounts. The universe contains built-in preferences that break perfect mirror symmetry. Researchers call this phenomenon CP symmetry violation, where charge conjugation and parity operations together don't preserve physical laws. The effect is incredibly subtle, but measurably real in laboratory experiments. These tiny asymmetries may explain why our universe contains matter rather than antimatter. Without some mechanism favoring matter production, equal amounts of cosmic twins would have annihilated completely during the early universe. The discovery revolutionized understanding of fundamental physics. Perfect symmetry represents an idealized concept rather than ultimate reality. Nature contains subtle biases that determine the composition of everything we observe. Scientists studied mysterious particles called kaons to test nature's symmetry rules. These unstable particles decay into other particles within fractions of seconds. Physicists expected kaons and their antimatter twins to behave identically. Careful measurements revealed shocking asymmetry in decay patterns. Neutral kaons and their antimatter partners behave slightly differently before decaying. The difference is minuscule but consistently measurable. This violation of symmetry occurs through the weak nuclear force, one of nature's four fundamental interactions. The weak force treats matter and antimatter slightly differently during certain decay processes. The kaon experiments proved that perfect mirror symmetry doesn't exist in nature. Some physical processes distinguish between matter and antimatter in subtle but important ways. These differences accumulate over cosmic time scales. This discovery provided the first experimental evidence for fundamental asymmetry in physical laws. The universe operates according to rules that favor matter over antimatter by tiny but crucial amounts. Our universe presents a profound puzzle. Early cosmic conditions should have produced equal amounts of matter and antimatter. These cosmic twins should have annihilated completely. Yet here we are, living in a matter-dominated universe. Scientists call this the baryon asymmetry problem. Baryons represent particles like protons and neutrons that form atomic nuclei. The universe contains vast quantities of matter baryons, but virtually no antimatter baryons. Current observations suggest that for every billion matter-antimatter pairs created in the early universe, one extra matter particle survived. This tiny surplus represents everything we can observe: stars, planets, galaxies, and life itself. The mechanism producing this cosmic imbalance remains one of physics' greatest unsolved mysteries. Something during the universe's first moments created a slight preference for matter over antimatter production. Understanding this asymmetry could reveal fundamental principles governing reality itself. The answer determines why we exist in a universe made of matter, rather than empty space filled only with radiation. Russian physicist Andrei Sakharov identified three conditions necessary for matter to achieve victory over antimatter in the early universe. Without all three factors operating simultaneously, perfect matter-antimatter symmetry would prevail. The first condition requires baryon number violation, processes that can create or destroy matter particles without maintaining perfect balance. Normal physics conserves baryon number strictly. Some exotic process must violate this conservation rule. The second condition demands departure from thermal equilibrium. The early universe must cool rapidly enough that particle creation and destruction processes cannot maintain perfect balance between matter and antimatter production. The third condition requires both charge conjugation and time reversal symmetry violations. Physical laws must treat matter and antimatter differently while also distinguishing between forward and backward time directions. These three Sakharov conditions provide a theoretical framework for understanding cosmic matter dominance. However, identifying specific mechanisms satisfying all three requirements remains an active area of research. Neutrinos represent nature's most abundant particles after photons. These ghost particles barely interact with normal matter. Trillions pass through your body every second without causing any effects. Yet neutrinos may hold keys to cosmic asymmetry. Matter neutrinos and antimatter antineutrinos exhibit a property called helicity, the relationship between particle spin and motion direction. Matter neutrinos spin left-handed relative to their motion. Antimatter antineutrinos spin right-handed. This represents a fundamental asymmetry in how nature treats matter and antimatter neutrinos. The weak nuclear force that governs neutrino interactions distinguishes completely between left-handed and right-handed particles. Recent discoveries suggest neutrinos can transform between different types during their travels through space. These oscillations might proceed differently for matter neutrinos versus antimatter antineutrinos. Such differences could contribute to cosmic matter dominance. Understanding neutrino asymmetries requires experiments with incredibly sensitive detectors. These elusive particles offer unique insights into fundamental symmetry violations that shaped our universe. Theoretical physics contains elegant symmetry principles that seem to require perfect equality between matter and antimatter. Charge conjugation symmetry states that reversing all electrical charges in any physical system should produce identical behavior. Under this symmetry rule, replacing every particle with its antimatter twin should create a universe that operates according to identical physical laws. Antimatter galaxies should form and evolve exactly like matter galaxies. Parity symmetry adds another layer of expected equality. This principle states that mirror reversing any physical system should produce equivalent behavior. Left-handed and right-handed processes should occur with equal probability. Combining charge conjugation and parity symmetries, called CP symmetry, should guarantee perfect matter-antimatter equality. The mathematical formalism provides no mechanism for distinguishing between cosmic twins. Yet experimental evidence clearly demonstrates CP symmetry violations in nature. The elegant mathematical symmetries don't perfectly describe reality. Subtle asymmetries allow matter to dominate our observable universe. Time reversal symmetry presents one of physics' most mind-bending concepts. This principle states that fundamental physical laws should remain identical whether time flows forward or backward. Antimatter provides a direct connection to this temporal symmetry. Antimatter-particle interactions can sometimes be mathematically viewed as normal matter interactions running in reverse temporal direction. An antimatter particle moving forward through time behaves, in this picture, like a matter particle moving backward through time. This temporal relationship suggests deep connections between antimatter and time itself. Studying antimatter interactions can hint at how physical processes would look if time flowed in reverse. In many cases, nature appears symmetric between forward and backward temporal directions. The time reversal symmetry helps explain why antimatter particles exhibit exactly opposite properties to their matter twins. Reversing temporal direction naturally inverts electrical charges, magnetic moments, and other particle characteristics. However, some weak force interactions violate time reversal symmetry, just as they violate charge conjugation symmetry. These violations provide additional clues about fundamental asymmetries that shaped cosmic evolution. Physicists discovered a profound symmetry that combines charge conjugation, parity reversal, and time reversal into one unified operation. This CPT symmetry appears to be perfectly preserved throughout all known physical processes. CPT symmetry requires that simultaneously reversing all charges, mirror-reflecting all spatial coordinates, and reversing time direction must leave physical laws completely unchanged. This represents one of the most fundamental principles in theoretical physics. Unlike individual symmetries that show violations in nature, CPT symmetry appears absolutely perfect. No experimental evidence exists for CPT symmetry breaking in any physical process. The combined operation maintains perfect cosmic balance. This preserved symmetry provides crucial constraints on possible explanations for cosmic matter dominance. Any successful theory must respect CPT symmetry while allowing individual CP and T symmetries to be violated. The CPT theorem represents one of the deepest insights into the mathematical structure underlying physical reality. It connects antimatter existence to fundamental spacetime properties in ways that continue to guide theoretical research. The most ambitious physics theories attempt to unify all fundamental forces within single mathematical frameworks. These grand unified theories predict exotic processes that could explain why matter defeated antimatter in the cosmic battle. Early universe conditions involved temperatures and energies far exceeding anything achievable in modern laboratories. Under these extreme conditions, distinctions between electromagnetic, weak, and strong nuclear forces disappear completely. Grand unified theories predict that matter and antimatter production rates could differ slightly during phase transitions in the cooling early universe. These microscopic asymmetries would accumulate over cosmic time scales. Some theories propose that heavy particles called X-bosons mediated interactions during the universe's first moments. These exotic particles could decay preferentially into matter rather than antimatter. Even tiny preferences would produce observable cosmic asymmetry. However, no experimental evidence confirms grand unified theory predictions. The energy scales involved exceed current technological capabilities by enormous margins. Testing these theories requires cosmic scale experiments that may never be feasible on Earth. Millions of medical patients receive antimatter-powered scans each year without realizing it. These machines use controlled antimatter annihilation to peer inside human bodies with incredible precision. The technology has quietly revolutionized modern medicine. The process begins with radioactive materials that naturally decay and produce antimatter particles called positrons. Medical technicians inject tiny amounts of these substances into patients through simple intravenous procedures. When antimatter positrons encounter electrons inside human tissue, they annihilate instantly and produce gamma rays. These high-energy light particles escape the body and travel to special detectors surrounding the patient. Computer systems analyze the gamma ray patterns to construct detailed three-dimensional images. Doctors can observe blood flow, organ function, and disease processes in real time. This technique reveals medical conditions that remain invisible to conventional X-rays. Scientists call this antimatter imaging process positron emission tomography. The antimatter doses are incredibly small and completely safe for patients. This represents antimatter's most successful practical application in the modern world. Traditional cancer radiation treatments damage healthy tissue surrounding tumors. Doctors needed precise tools that could deliver deadly energy directly to cancer cells without harming nearby organs. Antimatter-related particle beams have been explored for this kind of surgical precision. Positron and antiproton beam concepts use antimatter particles as microscopic bullets against cancer. In these approaches, much of the energy can be delivered near the tumor site rather than spread evenly through surrounding tissue. Annihilation can add extra local energy where the beam stops. This kind of targeting could allow doctors to deliver lethal radiation doses to cancer cells while minimizing side effects. The antimatter energy release happens where doctors want maximum damage. Healthy tissue can receive less exposure. The treatment requires specialized facilities with particle accelerators and magnetic beam steering systems. Only a few research centers worldwide possess the technology needed to study antimatter-based cancer therapy. The approach remains promising, but it is not yet a standard hospital treatment. This represents one of antimatter's most promising medical applications. The technique could revolutionize cancer treatment by providing unprecedented precision in radiation delivery. Doctors need ways to observe how drugs move through living bodies and how organs process different substances. Traditional methods require tissue samples or invasive procedures that disrupt normal body functions. Antimatter tracers solve this monitoring challenge. Scientists attach antimatter-producing isotopes to molecules that participate in specific body processes. These radioactive tracers behave identically to normal molecules but emit positrons as they decay. The antimatter signatures reveal exactly where the molecules travel. The antimatter annihilation creates gamma rays that escape the body without causing tissue damage. External detectors track these signals to map molecular pathways in real time. Scientists can watch drug distribution, metabolism, and organ function without disrupting natural processes. This technique revolutionized pharmaceutical research and medical diagnosis. Doctors can determine optimal drug dosages, identify metabolic disorders, and monitor treatment effectiveness. The antimatter signals provide information impossible to obtain through other methods. Antimatter tracing represents a perfect example of turning dangerous particles into beneficial medical tools. The same annihilation process that makes antimatter hazardous also makes it incredibly useful for biological monitoring. Manufacturing industries face constant challenges detecting microscopic flaws in metal structures. Traditional inspection methods miss tiny cracks and voids that can cause catastrophic failures. Antimatter-based analysis provides unprecedented sensitivity for defect detection. Positron annihilation spectroscopy exploits antimatter's unique interaction with metal crystal structures. Scientists inject positrons into metal samples and analyze the gamma rays produced during annihilation. Different annihilation patterns reveal specific types of structural defects. The technique detects voids smaller than individual atoms within metal crystals. These microscopic defects remain invisible to conventional inspection methods, including X-rays and ultrasound. Antimatter analysis reveals hidden flaws before they propagate into dangerous cracks. Industries use this technology to inspect critical components for aircraft engines, nuclear reactors, and medical implants. The antimatter-based analysis prevents equipment failures that could endanger human lives. Quality control reaches unprecedented levels of precision. This industrial antimatter application demonstrates how particle physics discoveries translate into practical engineering tools. The same exotic particles studied in research laboratories now protect public safety through superior materials analysis. Chemical rockets carry their own weight in fuel just to escape Earth's gravity. Reaching other stars requires propulsion systems far beyond current chemical technology. Antimatter offers the highest energy density possible for spacecraft propulsion. A single gram of antimatter contains more energy than thousands of tons of chemical rocket fuel. When matter and antimatter annihilate, they convert mass to energy with perfect efficiency. No other known energy source approaches this theoretical maximum. Antimatter rockets could accelerate spacecraft to significant fractions of light speed. This would reduce interstellar journey times from millions of years to decades. Mars missions could be completed in weeks rather than months. However, current antimatter production capabilities fall dramatically short of propulsion requirements. Creating enough antimatter to fuel even small spacecraft would require centuries using today's technology. Storage and handling present equally daunting challenges. These obstacles explain why antimatter propulsion remains theoretical despite its tremendous potential. Breakthrough advances in production and storage technology would be needed before antimatter rockets become practical reality. How much energy can different fuels store per unit of weight? This question determines the practicality of various energy sources for transportation and power generation. Antimatter provides the theoretical maximum energy density possible. Gasoline stores approximately 45 million joules per kilogram of fuel weight. Nuclear fission releases roughly 80 trillion joules per kilogram of uranium fuel. These represent humanity's most energy-dense practical fuels. Antimatter annihilation releases 90 quadrillion joules per kilogram. That is more than 1,000,000 times greater than nuclear energy. This represents complete conversion of matter to energy according to Einstein's famous equation. A single antimatter pellet the size of an aspirin tablet could power the entire US for several minutes. The same amount of energy stored in gasoline would require millions of gallons of fuel. No other energy source can match antimatter's storage efficiency. These numbers explain scientific interest in antimatter energy applications despite current technological limitations. Mastering antimatter storage and handling could revolutionize human energy systems. Interstellar distances strain human comprehension. The nearest star system lies over 4 light-years away. That journey would require thousands of years using conventional propulsion. Antimatter technology could shrink these cosmic distances to human scales. Antimatter engines could accelerate spacecraft to 10% of light speed or higher. This would reduce travel time to the nearest stars from millennia to decades. Human crews could complete interstellar journeys within single lifetimes. The propulsion system would work by directing antimatter annihilation energy through magnetic nozzles. The resulting particle beam would provide thrust far exceeding anything achievable with chemical or nuclear propulsion. Spacecraft could achieve constant acceleration for months. Advanced antimatter engines might enable travel to 20% of light speed or beyond. This would open the entire local galaxy to human exploration. Civilization could spread among the stars within centuries rather than millions of years. However, these capabilities require antimatter quantities far beyond current production levels. Creating sufficient fuel for interstellar missions remains an enormous technological challenge that may require centuries to solve. Nuclear power plants generate radioactive waste that remains dangerous for thousands of years. Current storage solutions require geological isolation for longer than human civilization has existed. Antimatter technology has been proposed as a potential solution to this persistent problem. In theory, antimatter bombardment could trigger nuclear reactions that alter some radioactive nuclei. This could shorten the dangerous lifetime of certain waste products. It remains a speculative idea rather than a working waste treatment system. This process could, in principle, reduce some nuclear waste storage times from millennia to much shorter periods. Highly radioactive materials might become safer on more human timescales. But the real-world effectiveness would depend on the isotope and the engineering method. However, the antimatter quantities required for waste processing exceed current production capabilities by enormous margins. Creating sufficient antimatter for nuclear waste treatment would require revolutionary advances in production technology. The theoretical possibility demonstrates antimatter's potential for solving humanity's most persistent technological challenges. Mastering antimatter manipulation could eliminate problems that have puzzled scientists for generations. Studying antimatter provides unique insights into the deepest principles governing our universe. These particles offer experimental access to questions that cannot be answered through any other means. Fundamental physics discoveries often emerge from antimatter research. Antimatter experiments test whether the basic laws of physics remain identical when matter and antimatter switch roles. Scientists call this fundamental symmetry charge parity time reversal. Discovering violations of this symmetry could revolutionize theoretical physics. The techniques developed for antimatter manipulation advance multiple scientific fields simultaneously. Magnetic confinement, ultra-high vacuum technology, and precision measurement systems find applications throughout experimental science. Antimatter research pushes engineering capabilities to absolute limits. Creating devices that function under these extreme conditions requires innovations that often benefit entirely different technologies. Particle physics laboratories become proving grounds for advanced engineering. The knowledge gained from antimatter studies could unlock technologies currently beyond imagination. Understanding matter's fundamental nature provides the foundation for manipulating reality at the most basic level. Imagine a future civilization that has solved antimatter's production and storage challenges. What becomes possible when humanity masters the ultimate energy source? The implications extend far beyond current technological dreams. Energy becomes essentially unlimited when antimatter conversion reaches industrial scales. Climate change, resource depletion, and energy poverty could become historical problems rather than ongoing challenges. Human civilization could transcend planetary energy limitations. Space colonization becomes economically feasible with antimatter propulsion systems. The solar system transforms into humanity's local neighborhood rather than a distant frontier. Interstellar expansion could begin within centuries rather than millennia. Terraforming planets becomes possible using antimatter energy sources. Atmospheric modification, climate engineering, and geological restructuring could transform barren worlds into Earth-like environments. Humanity could actively create habitable planets. However, these advances require breakthrough discoveries that may take centuries to achieve. Current antimatter technology represents the first tentative steps toward mastering matter's ultimate energy potential. The journey from laboratory curiosity to civilization-transforming technology remains long and uncertain. Antimatter production represents the worst energy investment in human technology. Current methods require astronomical energy inputs to create microscopic antimatter quantities. The energy return approaches 0% efficiency. The world's most powerful particle accelerators consume massive amounts of electricity to generate tiny numbers of antimatter particles. Creating enough antimatter to power a small light bulb for 1 second would require running these machines continuously for millions of years. Scientists estimate that producing a single gram of antimatter would consume more energy than the entire United States uses in several years. The electricity costs alone would exceed trillions of dollars at current power prices. This crushing inefficiency stems from fundamental limitations in particle acceleration technology. Most of the energy invested in antimatter creation gets wasted as heat, stray radiation, and particle losses. Only a tiny fraction actually creates usable antimatter. The energy economics make antimatter completely impractical for any large-scale applications. Until revolutionary breakthroughs occur in production efficiency, antimatter will remain confined to laboratory research and medical applications requiring microscopic quantities. Engineers face an ultimate containment challenge when attempting to store antimatter for extended periods. The substance must remain completely isolated from all normal matter. Even single-atom contacts trigger instant annihilation and total material loss. No known technology can provide perfect matter isolation under real-world conditions. Temperature fluctuations, mechanical vibrations, and electromagnetic interference constantly threaten containment system stability. Any disruption causes immediate antimatter loss. Current storage records measure antimatter containment in minutes or hours rather than days or weeks. Maintaining stable magnetic fields and ultra-high vacuum conditions requires continuous energy input and active control systems. Long-term antimatter storage demands isolation perfection that exceeds human engineering capabilities. The technical requirements approach theoretical limits imposed by quantum mechanics and thermodynamics. Perfect isolation may be fundamentally impossible. These storage limitations prevent antimatter accumulation for practical energy applications. Using antimatter as fuel requires containment periods measured in months or years. Current technology falls dramatically short of these demanding requirements. How much would antimatter cost if available for purchase? Economic estimates reveal price tags that dwarf any other material on Earth. Antimatter production costs make diamond and gold seem practically free. Creating 1 gram of antimatter using current technology would cost approximately $100 trillion. This price reflects the enormous energy requirements and infrastructure costs involved in particle acceleration and magnetic containment. The production expenses include massive facility construction, continuous electricity consumption, specialized equipment maintenance, and highly trained personnel. These costs accumulate over years of operation to produce microscopic antimatter quantities. Individual antimatter atoms are extraordinarily expensive to create and store in practice. This represents the most expensive manufacturing process in human history. The price per usable sample reaches levels that exceed the gross domestic product of small nations. These prohibitive costs explain why antimatter research remains limited to government laboratories and major universities. Private industry cannot justify investments with negative returns measured in trillions of dollars. What happens when antimatter containment systems develop tiny flaws? Even microscopic leaks can trigger catastrophic energy releases that destroy expensive research equipment. The margin for error approaches absolute zero. Antimatter annihilation produces intense gamma radiation that damages nearby materials and electronics. Small containment failures can flood entire laboratory buildings with damaging radiation. Equipment worth millions of dollars becomes unusable. The energy release from minimal antimatter quantities seems surprisingly modest until concentrated into small spaces. A containment breach involving even tiny antimatter quantities can damage sensitive equipment, and larger amounts can melt through metal structures. Emergency shutdown systems must operate faster than human reaction times to prevent cascading failures. Automated monitoring detects containment parameter deviations and triggers protective responses within milliseconds. These safety challenges require multiple redundant containment systems and extensive radiation shielding. The precautions add enormous complexity and cost to antimatter research facilities while never guaranteeing complete safety. Does antimatter respond to gravity like normal matter, or does it experience some exotic gravitational effect? This fundamental question has puzzled physicists for decades. The answer could revolutionize physics or confirm existing theories. Most physicists expect antimatter to fall downward in Earth's gravitational field, just like normal matter. Einstein's general relativity theory predicts identical gravitational responses for all forms of matter and energy regardless of electrical charge. However, some theoretical models suggest antimatter might experience reversed gravitational forces. If antimatter actually falls upward, it would represent the most revolutionary discovery in modern physics. Current theories would require complete revision. Testing antimatter's gravitational response requires incredibly delicate experiments. Gravitational forces are incredibly weak compared to electromagnetic effects. Isolating pure gravitational influences on charged antimatter particles presents enormous technical challenges. Current experimental results remain inconclusive due to technical limitations. Determining antimatter's true gravitational behavior requires more sensitive equipment and better isolation techniques that may take decades to develop. Charged antimatter particles can be manipulated using magnetic and electric fields. Scientists can push, pull, and steer these particles using electromagnetic forces. Neutral antimatter presents an entirely different challenge. Neutral antimatter atoms carry no electrical charge and ignore electromagnetic fields completely. Traditional magnetic bottle containment becomes useless. Electric field manipulation has no effect on neutral particle motion. Antihydrogen atoms, the simplest neutral antimatter, drift freely through magnetic containment systems. They cannot be steered, focused, or controlled using conventional techniques. Most neutral antimatter escapes confinement within seconds. Scientists explore exotic containment methods including gravitational traps, laser manipulation, and magnetic gradient confinement. None of these experimental techniques works reliably for extended storage periods. The neutral antimatter control problem represents one of the most challenging engineering obstacles in antimatter research. Solutions may require entirely new physics principles or technologies that do not currently exist. Antimatter storage requires vacuum conditions approaching absolute perfection. Even trace amounts of residual gas cause immediate annihilation and particle loss. Creating these ultra-pure environments pushes vacuum technology to theoretical limits. The best vacuum systems can remove gas molecules down to incredibly low densities but never achieve complete emptiness. Quantum fluctuations, thermal motion, and material outgassing constantly introduce trace contamination. Vacuum chambers require continuous pumping to maintain ultra-low pressure conditions. Multiple pump stages operate in series to achieve progressively cleaner vacuum. Power consumption for vacuum maintenance often exceeds the energy content of stored antimatter. Even microscopic amounts of oil vapor, moisture, or dust particles destroy antimatter instantly upon contact. Vacuum chamber cleanliness must exceed surgical operating room standards by enormous margins. The vacuum requirements approach fundamental limits imposed by quantum mechanics. Perfect emptiness may be impossible to achieve in practice. These limitations constrain antimatter storage duration regardless of magnetic containment improvements. How can scientists measure antimatter particle properties without destroying the particles during measurement? This experimental paradox limits detailed antimatter research. Every measurement technique involves some form of matter-antimatter interaction. Traditional particle detection methods work by having particles interact with detector materials. These interactions provide measurement data, but also destroy the antimatter sample. Scientists must choose between detailed measurements and sample preservation. Non-invasive measurement techniques, like laser spectroscopy, offer partial solutions but provide limited information. Obtaining complete particle characterization requires direct interactions that annihilate the antimatter being studied. Sample sizes remain so small that even gentle measurement procedures destroy significant portions of available antimatter. Each experimental measurement reduces the material available for subsequent studies. This measurement dilemma slows antimatter research progress and increases experimental costs. Scientists must design experiments carefully to extract maximum information from minimal antimatter samples before inevitable destruction. Current antimatter production relies on massive particle accelerators designed for physics research rather than industrial manufacturing. These facilities cannot scale up to produce commercially useful quantities without revolutionary technological advances. Particle accelerators achieve high antimatter production rates only during brief collision events. The machines operate intermittently and require extensive maintenance between experimental runs. Continuous industrial production demands entirely different equipment designs. Alternative production methods remain purely theoretical. Scientists have proposed various schemes including solar power satellites, fusion-powered accelerators, and exotic matter manipulation techniques. None of these approaches exists beyond computer simulations. Manufacturing antimatter in useful quantities would require energy sources far exceeding current global power generation capacity. The infrastructure needed for large-scale antimatter production exceeds any industrial project in human history. Revolutionary breakthroughs in energy generation, particle acceleration, and magnetic containment would be necessary before antimatter manufacturing becomes remotely feasible. These advances may require centuries of technological development. Who controls antimatter research and development around the world? Currently, no international treaties or safety standards specifically address antimatter technology. This regulatory vacuum creates potentially dangerous oversight gaps. Antimatter research proceeds under general laboratory safety guidelines designed for conventional radioactive materials. These existing regulations do not address the unique hazards posed by matter-antimatter annihilation events. Different nations maintain varying standards for antimatter research safety protocols. This inconsistency could lead to inadequate safety measures or competitive pressure to reduce protective precautions. International coordination remains minimal. The potential military applications of antimatter technology raise serious security concerns. No international agreements specifically address antimatter weapons development or proliferation to hostile organizations. As antimatter research advances, the lack of specific regulatory frameworks becomes increasingly problematic. Developing comprehensive international safety standards requires cooperation between scientists, governments, and international organizations that has not yet materialized. Imagine traveling to the nearest star system in less than a human lifetime. Current chemical rockets make this journey impossible within any reasonable time frame. The trip would require thousands of years using conventional propulsion technology. Antimatter engines could change everything. These revolutionary propulsion systems would accelerate spacecraft to significant fractions of light speed. A journey to Proxima Centauri could be completed in decades rather than millennia. Interstellar exploration would become achievable within single human generations. The spacecraft would work by directing antimatter annihilation energy through magnetic nozzles. This creates particle beams with far greater thrust than any chemical or nuclear propulsion system. Constant acceleration for months would build tremendous velocities. Advanced antimatter rockets might achieve 20% of light speed or higher. This would transform the entire local galaxy into humanity's neighborhood. Star systems within 50 light years could be reached during normal career spans. However, these capabilities require antimatter fuel quantities far beyond current production abilities. Creating sufficient propellant for interstellar missions remains one of the greatest technological challenges humanity has ever faced. Energy scarcity has driven human conflict throughout history. Nations fight wars over oil reserves, coal deposits, and uranium supplies. These finite resources cannot sustain growing global energy demands indefinitely. Antimatter offers unlimited energy independence from traditional fuel sources. Complete matter-energy conversion provides the highest possible energy density. No other power source can match antimatter's theoretical energy yield. A few grams of antimatter could power entire cities for extended periods. The same energy stored in fossil fuels would require millions of tons of coal or oil. Antimatter makes traditional energy resources look primitive by comparison. Clean antimatter power produces no atmospheric pollution or radioactive waste products. The only byproduct of matter-antimatter annihilation is pure energy in the form of controllable radiation. Environmental impact approaches zero. Mastering antimatter energy technology could eliminate resource conflicts and provide abundant clean power for developing nations. However, achieving practical antimatter energy systems requires revolutionary advances in production and storage that may take centuries. Terraforming represents humanity's ultimate environmental engineering challenge. Converting lifeless planets into Earth-like environments requires energy resources far exceeding current capabilities. Conventional technology cannot provide sufficient power for planetary-scale climate modification. Antimatter energy could make terraforming economically feasible for the first time. The enormous energy release from matter-antimatter annihilation could drive atmospheric processes, magnetic field generators, and global warming systems. Planetary atmosphere composition could be modified using antimatter-powered chemical processes. These systems would convert carbon dioxide to oxygen while removing toxic gases. Atmospheric pressure and temperature could be adjusted to Earth normal ranges. Antimatter explosions could trigger volcanic activity to release trapped gases and create more substantial atmospheres. Carefully controlled detonations would avoid planetary damage while reshaping global climate systems. Advanced civilizations might use antimatter technology to create entirely artificial planets from asteroid materials. The energy requirements for such massive construction projects would demand antimatter power sources operating at industrial scales. Current antimatter experiments test the most fundamental principles governing our universe. These studies probe whether the deepest physical laws remain identical when matter and antimatter exchange roles. Revolutionary discoveries could emerge from such investigations. Antimatter research pushes measurement precision to absolute limits. Scientists develop incredibly sensitive detection systems and ultra-stable containment technologies. These advances often find applications in completely different scientific fields. The techniques for creating and manipulating antimatter require understanding physics at the most fundamental level. Mastering these processes could unlock technologies that seem impossible using current knowledge. Detailed antimatter studies might reveal new particles or forces that don't interact with normal matter. These discoveries could revolutionize theoretical physics and open pathways to exotic technologies like faster-than-light communication. Understanding antimatter's relationship to gravity, time, and space could provide insights into the universe's deepest structure. These discoveries might enable manipulation of fundamental forces that govern reality itself. Throughout history, certain technologies have triggered rapid societal transformation periods. The printing press revolutionized information distribution. Steam engines enabled industrial civilization. Computer networks created the digital age. Antimatter technology could represent the next great civilization-changing breakthrough. Mastering matter's ultimate energy source would enable technologies currently beyond imagination. The societal implications would dwarf previous technological revolutions. Unlimited energy availability would eliminate most current technological constraints. Manufacturing processes that seem prohibitively expensive today would become economically viable. Material abundance could replace resource scarcity as civilization's organizing principle. The transition period might unfold faster than societies can adapt to rapid change. Historical technological revolutions required generations for social adjustment. Antimatter-enabled changes might occur within decades. Managing such rapid transformation would challenge human institutions designed for slower change rates. The social disruptions could be profound even if the ultimate benefits prove transformational for human civilization. Astronomers search for signs of intelligent life throughout the galaxy using various detection methods. Radio signals, artificial structures, and atmospheric modifications might reveal alien civilizations. Antimatter utilization could provide the most definitive proof. Large-scale antimatter production would generate distinctive energy signatures detectable across interstellar distances. Advanced civilizations using antimatter power would emit characteristic radiation patterns during industrial operations. The energy scales involved in serious antimatter utilization would dwarf natural stellar processes. Alien antimatter facilities might outshine entire star systems during peak operation periods. These artificial energy sources would be unmistakable. Scientists propose that antimatter mastery represents a crucial developmental milestone for any technological species. Civilizations that achieve controlled antimatter production gain access to unlimited energy and interstellar travel capabilities. Detecting antimatter signatures from other star systems would prove that intelligence can overcome the same technological barriers currently limiting human civilization. Such discoveries would revolutionize our understanding of cosmic development patterns. Einstein's theories suggest that manipulating space-time curvature could theoretically enable time travel effects. Such experiments would require enormous energy concentrations to warp space and time significantly. Antimatter provides the ultimate energy source for exotic physics research. Theoretical physicists have proposed various time manipulation schemes, including rotating black holes, cosmic strings, and traversable wormholes. All these concepts require energy densities far exceeding conventional power sources. Antimatter annihilation could provide sufficient energy to create significant spacetime distortions in laboratory settings. These experiments would test whether time travel remains purely theoretical or becomes achievable through advanced engineering. The energy released during controlled antimatter reactions approaches levels that might affect the flow of time itself. Creating microscopic time dilation effects could become possible with sufficient antimatter fuel supplies. However, such experiments would be incredibly dangerous and might violate fundamental physical principles. The risks associated with time manipulation experiments could threaten causality and logical consistency throughout the universe. What if empty space itself could become a source of raw materials for advanced manufacturing? Quantum physics reveals that vacuum contains enormous amounts of virtual particle pairs constantly appearing and disappearing. Antimatter-powered systems might provide sufficient energy to convert virtual particles into permanent matter. This would enable manufacturing processes that create materials directly from empty space, rather than mining planetary resources. The technique would work by using intense antimatter energy fields to separate virtual particle pairs before they can annihilate. The resulting matter and antimatter could be captured and used as manufacturing feedstock. Advanced civilizations might use this technology to construct massive space structures without transporting materials across interstellar distances. Entire planets could be assembled from vacuum-extracted matter using antimatter energy sources. Such manufacturing capabilities would make resource scarcity obsolete for civilizations possessing adequate antimatter production technology. The universe's vacuum would become an unlimited supply depot for any conceivable construction project. Why does our universe contain matter rather than empty space filled only with radiation? This fundamental question drives much current antimatter research. The answer could reveal the deepest principles governing cosmic structure. Early universe conditions should have produced equal amounts of matter and antimatter. These cosmic twins should have annihilated completely during the first moments after the Big Bang. Yet matter clearly dominates everything we observe. Understanding this cosmic asymmetry requires detailed antimatter studies under controlled laboratory conditions. Scientists hope to discover the subtle physical processes that favored matter over antimatter during cosmic evolution. The research investigates whether fundamental physical laws remain truly symmetric or contain hidden preferences. Any discovered asymmetries could explain how complexity and structure emerged from primordial simplicity. These discoveries would illuminate the chain of events that led from the Big Bang to galaxies, stars, planets, and ultimately life itself. Antimatter studies provide unique insights into the universe's architectural blueprint. Imagine looking up at an antimatter night sky filled with antimatter stars orbiting antimatter planets. Antimatter beings might wonder why their universe contains antimatter instead of the exotic substance they call matter. This thought experiment highlights one of existence's deepest mysteries. Why do we find ourselves in a matter-dominated cosmos rather than an antimatter-dominated one? The answer touches fundamental questions about reality itself. The question extends beyond physics into philosophy and metaphysics. If the universe began with perfect matter-antimatter symmetry, some mechanism must have broken this balance. Understanding this process approaches the ultimate explanation for existence. Current theories suggest that the matter-antimatter asymmetry required incredibly precise conditions during the universe's first moments. The probability of achieving exactly the right balance seems astronomically small. Yet here we are, living proof that the cosmic dice rolled in favor of matter over antimatter. Antimatter research continues searching for the fundamental principles that determined why we exist rather than eternal emptiness. The ultimate answer may reveal the deepest secrets of reality itself.